So we'll go into that and it'll be really cool because a lot of resources actually don't, or at least they didn't when I was learning computer vision. So, all right, so this is computer vision, build your own object detector and data sets. And you can follow me in all these places and check out Six Skill, the company I work for, at all these places. I'll share out the links as well. Oh, actually, right before we go any further, let me share this in the chat. So this is just kind of all those links that you might need here. And really the main thing is just sign up for the free account there, the free trial for the data annotation tool. That's what we're going to be using today. And then you'll be able to follow along. So that's really the only thing you actually have to do to follow along. Otherwise, everything else is just going to be online. The labeler is online as well. You just have to sign up. It'll send you a verification email. Once you're verified, then you'll be able to do data annotation. All right, and I hit recorded. I have the slide up because I often forget. All right, setup. So we'll be using an online data science coding environment called Google Colab. You just need a Google account for that because it is a tool made by Google. And then you need a modern web browser like Chrome, and then the Sense data annotation tool is what we're going to be using to create our own data sets. So again, you can just sign up there. What this workshop is, hopefully a super friendly introduction to computer vision, kind of with no previous experience expected, but knowing some Python will probably be helpful when we get to the coding section. But don't worry if you haven't done a lot of Python or even coding in general. I have a lot of code written in there that you'll be able to run. And even if you don't understand exactly what's happening, I will explain what's going on. But you'll also be able to run all the code and actually leave this workshop with a trained model yourself, even if you haven't done a lot of programming before. So we'll cover kind of at a high level the applications and basic intuition of computer vision. Then we'll go into how to label your own data, and then jump into coding and training a model with Python and a Python library. And keep in mind, you can't learn everything in 2 hours, especially in a field as big and complicated as computer vision and deep learning. But you can learn enough to get started and excited about computer vision and actually start using it right away. And if you have a problem in mind for work or a personal project, hopefully you can leave this workshop and actually just start working on it and be able to get pretty far, if not accomplish what you want to do. So parts of it might feel fast-paced or challenging, depending on your background. That's okay. You'll learn a lot by sticking through it. And then a big thing is to keep learning after this workshop. So I'll point to some resources afterwards if you want to continue your computer vision journey. So a little bit about me. My name is Sage Elliott. I'm a machine learning engineer and developer evangelist at sixskill.com. We do really, really cool stuff. Let me share this link if you want to check us out. We do really cool stuff with computer vision, machine learning, and IoT. So like actually managing devices to run things like computer vision, machine learning on across a whole bunch of different industries. And then we're also making tools to make it easier for everyone to create and deploy things like computer vision models across a whole bunch of different fields. For about the past decade, I've worked as either a software or a hardware engineer with startups and agencies in Seattle, and then also in Central Florida, if anyone happens to be from there. A lot of times someone is in the workshop, and it's always fun to be like, they're like, I lived exactly in Melbourne, Florida too. I love making things with technology, and you can stay connected with me at sageelliott.com. That kind of has links to everything. At Sage Codes on Twitter, or just find me on LinkedIn. You can search for Sage Elliott, 2 L's and 2 T's, and we can become connections. It's also a good place to stay connected with me if you have any questions after this workshop or anything. If you get stuck on labeling or training, feel free to ping me there. So a little bit about you. Normally doing in-person events, I'd love to, you go around the room and introduce yourself. But since the RSVP for this is pretty high and we're not in person, if you just want to put in the chat, where you're watching this from, it's always really cool to see where everyone's watching from. And then also why you're interested in computer vision. If you want to throw that in the chat real quick, it's always really fun to hear from everyone. And also, so you can connect with me on LinkedIn, but also there's a Slack channel here. This is a good place to also stay connected. So a lot of people will ping me on there or share in one of the channels. If they get stuck labeling or training a model, it's a great place to just, feel free to tag me, be like, hey, Sage Elliott, this label thing isn't working. Do you have any opinions on how I could overcome it? There's also an introductions channel. So if you want to introduce yourself to more people and stay connected, I really miss doing that in person. So I'm trying to kind of do it through the Slack channel. It's not quite the same, but it's kind of the best alternative I could come up with, this and LinkedIn from meeting people in person and see what you're working on. David said, watching from St. Paul, Minnesota, USA on Earth. Oh God, I thought it was going to be the other St. Paul, Minnesota, not the one on Earth. But then, so it said Vancouver, BC. Awesome. I went to Vancouver like I don't know, some point before, well before quarantine, like the year before. Really cool. I liked spending time up there. I would be excited to go back up there again. Cool. Anyone else want to put it in the chat where they're watching from? Feel free to go ahead and do that. I'm just going to keep moving on the slides for now. So a setup repeat for anyone who just arrived. I do see some more people came in. So we'll be using a online data science coding environment called Colab again. So you just need a Google account, modern web browser, and then just go ahead and sign up for the data annotation tool here. This is the tool we'll be using today. All the concepts and like theory and stuff, we'll be able to transfer across to like labeling almost any data set and also labeling with different tools and stuff. Someone said Fresno, California. Awesome. All right, so what is computer vision? So it's a pretty big field, but basically I'd boil it down to how computers gain understanding from images or videos. And there's other types of data that could be considered or turned into an image or video. So I think it was Brandon, I think that was your name. You were talking about, doing computer vision, but for audio, because you can use, I think it's a spectrogram is what it's called, where you translate, audio into a visual, like you've probably seen visualizations of audio, like people talking or music or anything like that. You can actually use computer vision to look at that and kind of in the same way that we're going to train it to do object detection on images, you can also train it to detect specific sounds with patterns in visualization. So here's a quick little demo that we have. You can see that it's tracking this truck right here. It's also seeing all these other trucks. And just noting a couple things. So it's drawing a box around where it thinks the truck is. And then it's also drawing pixels exactly where it thinks the truck is. So this little box kind of generalizes, hey, I think an object is within this rectangle. And then here we get really, really precise, saying, I think this is the exact pixels of the truck. And I'll talk about kind of why you'd want to use these different things in a little bit. And then you can also see we have another little layer to our algorithm that actually sees when a truck is moving versus when it's parked. So this is like saying, hey, like, is this truck moving or not? And it paints it green. Versus being parked, it'll paint it red. And that way you can also do things like, calculate how long a truck has been sitting there. So this is kind of a concept for like a rest stop, right? Like how long are trucks hanging out here? And you can see it's not detecting cars, it's only detecting trucks. So this is a model trained on trucks. One reason why I really like computer vision is it's a really, really cool interface into the world. And we're already doing amazing things with it today. Like if you look at all the different companies and things happening right now in the world, like there's just some really cool stuff happening with computer vision that's not just research, that's actually deployed in the fields. So who uses computer vision? More and more companies are using across just a whole bunch of different fields. So I'm just going to talk about some here. Amazon Go. Has anyone been in Amazon Go before? So we have several in Seattle. They're a new store. I know they're in some other states. And it's a kind of like a convenience store. They have a bigger one as well called Amazon Go Grocery. And it uses computer vision throughout the entire store. Like if you look up, there's just giant arrays of cameras and like GPUs looking at everything. And what happens is you walk in, you scan a QR code on your phone, it tracks you, and then it sees what you pick up, and then you walk out the store and it automatically charges you for those things you picked up. There is no checkout or anything like that. You just go in, you pick stuff up, and then you walk out. And it kind of feels like you're stealing, but it's really, really cool. They're working on delivery robots, self-driving cars. They just bought a company called Zoox last year, or this year, I think it was last year. And then also product listings. This is one I don't really think about, or I hadn't thought about a lot, but they have a ton of images that get uploaded to their site all the time. So they can actually look at those images, make sure they're appropriate for the product being listed, and things like a potential counterfeit stuff as well. Google Photos, YouTube content filtering. YouTube has so much data uploaded like every minute that you can't have a human look at everything. So you have to have algorithms do it, or computer vision models. They're also working on self-driving cars, Tesla, self-driving cars, Facebook, face tagging. These are all kind of examples that maybe you've seen or thought of, and like maybe you've even interacted with these things before. And then I want to point out some really, really cool fields that not everyone thinks about when you're getting started in something like computer vision. So you have agriculture. You could do things like crop monitoring, animal monitoring, construction, monitoring the site, how fast it's going up. Product safe, or people safety is a big deal there too. Like, are people wearing hard hats? Are they in a zone they shouldn't be? Self-driving tractors. There's a company I saw working on that, which I think sounds really cool. Going around like picking up dirt from somewhere and automatically bringing it to a different place in the work site is really cool. Manufacturing. This is actually how I got into computer vision, was doing a manufacturing quality assurance problem. That's a big thing right now. Can I have a machine just look at a product and tell me if it's good or bad, or detect like specific areas of damage that you could have someone fix, or like, are solder joints good or are they bad? Measuring throughput, supply chain. Oil and gas is really cool too. You can do leak detection. Again, safety for employees, like, are they wearing the appropriate gear? Are they in zones they shouldn't be? And then healthcare is amazing. The stuff, seeing the stuff in there is just always so awesome. Like, you have X-ray diagnostics, MRI scans, medicine research. And this is by no means everything. So if anyone has a field that they're really excited about, please put in the chat, or if there's something you're working on, or even if it's just one of these. Actually, if you just want to say what field you think is the most exciting, let me know in the chat, because I would love to hear it. And it's always really cool seeing what people are working on, or fields that I didn't list here that I kind of forgot about. Or it could be one that's in here that you're just really excited about. Like, if you're like, yeah, I want to get into healthcare and use computer vision to like look at MRI scans and help like save lives, I think it's really exciting. Anyone have any specific areas? There's quite a few people here, but the chat's pretty quiet. Not that you have to chat, but it's more fun if you do. I guarantee it. One person should at least have something they're excited about. Manufacturing is pretty cool because there's a lot of different products too, right? And a lot of, at least as someone who's worked it a lot in manufacturing, when I've been a hardware engineer in several companies, there's a lot of really interesting areas you can help improve manufacturing. Someone said they think healthcare and agriculture is the most exciting. I think those are really, really cool. We actually do a lot of work in agriculture. Actually, along a lot of these different verticals, we do some work with at SigSkill, which is really cool. Manufacturing and edge computing. Yeah, again, really cool. I like manufacturing. I have a soft spot for it because I worked a lot in the manufacturing world. So it's really cool being able to solve these problems I had a long time ago, which is awesome. So it says self-driving cars. That is super cool. Collision detection. Yeah. Yeah, self-driving cars is awesome. I'm really excited to see what happens in that field in the next 5 to 10 years. Cruise is doing really, really cool stuff. Google Waymo, Tesla, really excited to see what happens. All right, so you can keep putting stuff in there. I love hearing your comments on it, but I'm going to move on to the next slides now. So computer vision and deep learning. Computer vision isn't always tied to deep learning, but in the past decade or so, deep learning in the field of computer vision has been dominating all the complex problems. So anytime you see something in the news or from a big company, chances are that they're using deep learning. Like if you see something, them solving a cool computer vision problem, chances are they're using deep learning. And so like at a very high level, this is how it works. And most tutorials, if you've never done anything with deep learning or computer vision, they'll like start out and go way deeper into this. But this is all you need to know really to get started, just so you understand why we're labeling data and how it works at a high level. So imagine we have this function. You can imagine it a mathematical function or a programming function. And we want to teach this how to recognize a specific object, or if we're doing classification, like what's in this image. So let's say, for example, a classic example is you're doing classification where you would feed a computer vision model a picture of a cat or a dog, and it would predict, is it a cat or a dog? So to train it, we would do supervised machine learning where we feed it a whole bunch of images of cats and dogs, and each image has a label tied to it. So it'll learn, hey, this image is a dog, try to pick up some features that make a dog out of this. And then versus this is an image as a cat, kind of learn the differences between the dog and cats. So it might learn to pick up their noses look different, their snouts are different, the faces shapes are different, the ears are different, all these different things. It can pick up on so many different attributes of different classes. And so we would feed it through a whole bunch of times. It could be hundreds or thousands of times, and it'll learn from that data. Then we'll feed it a new piece of data, one that it's never seen before, an image it's never seen before, of a cat or dog in this case. And then it would return a prediction, and hopefully it would be correct. So it'll learn from a whole bunch of images with labels, and then we'll feed it a new image, and then it will say, hey, I think that's a cat or a dog. And so the cool part is like trying to program something very explicitly is really hard to say if this is a cat or a dog. Like, how would you do that, right? You'd be like, well, a cat has these shapes of ears, but like its eyes look like this, and its nose looks like this, and there's a ton of variations to that. So it's really hard to explicitly program. So in this case, we're using deep learning, and it learns those features by itself. So I'll share a couple links in the chat if you do want to check these out later. This one is just kind of a cool representation of a neural network if you've never done deep learning before. And this one's a cool visual representation of a convolutional neural network, which is a common type of neural network used in computer vision. But don't worry, you don't have to go look at those right now if you don't want to, just if you want to later. So a note on transfer learning. With most popular deep learning frameworks, you can preload, you can load pre-trained weights into your network. These have been trained on a ton of examples of like objects and animals and people and stuff like that. And then you can take those pre-trained weights and then feed it your new data set and adjust certain parts of the neural network. And it turns out that doing that usually means that your new neural network, like detecting new objects, learns much faster. So we're going to use this today, and it's very common to use it. You can really just think of it as not starting from zero, and I'll point it out in the code when we get there of like, this is the part where we're importing those weights. So just think of it, transfer learning means you're not starting from zero. And so you'll see today, we're going to train an object detector on just a couple hundred images and only like a few hundred cycles through those images, and it'll actually work really, really well. The reason why it's so fast is because we're going to be using something called transfer learning. And just a quick note, so if you're going to do like a hobby project after this or something, a good kind of rule of thumb, and by no means do you have to follow this, but I try to get something like 200 images or 200 instances. So if you had an image and there was 2 objects in there that we want to train on, that would count as 2, just to try to get a good baseline for your model. But it does really depend on your data type and how complex it is and how much variation there is. But just if you're collecting images after this, or you have a data set, I'd suggest starting with something like 200, but you could start with less. And then the more data, typically the better. The more data and more variations, the better. All right, so some types of computer vision. Computer vision is a very big field, and we're just going to focus on some types with deep learning. And many of these could be combined together or with other algorithms after the fact to get various outcomes. And we can talk about this kind of as we go. Let me see in the chat. I see a couple questions real quick. Someone said how to do computer vision with Android mobile app. Oh yeah, so there's we can talk a little bit about that. Let me get through this. But yeah, there's ways of training a model, and then you need to get that model on an Android app or have it on an API. Do requests from the Android app and then get the prediction. All right, so classification. We talked about this, doing it with the cats or dogs. Right, where you typically train on a whole image or a cropped portion of the image. And here I built a classifier to detect dog breeds. So this one predicted Labrador Retriever. You train on hundreds of images. And most tutorials will start here and cover classification very thoroughly, but I think object detection is much more exciting and actually allows you to do more stuff right off the bat. So one problem here is if we had a Chihuahua back here, it might get confused because the classifier would be like, cool, there's a dog. Maybe it would still predict Labrador Retriever because it's so big in the image, but the Chihuahua, it just might not really understand that it's there, or it won't understand where it is in the image. So object detection, this is what we're going to build today. Object detection can classify and localize where an object is inside the image or video. So here, right, it's not just saying goose or geese are detected. It's actually saying, hey, I think there's a goose here, and drawing a box around it. And then same with this one, saying, hey, there's a goose here, and I'm drawing a box around it. I think it's right here. And from here, you can do lots of really cool stuff, like count how many animals are in the frame. How close are they to each other? You could do some like simple math, like if you know the angles of the cameras and stuff, you can actually make kind of predictions of like, you know, how distance, are these geese 6 feet apart or not? And draw like a line between it. Or are they interacting with other objects in the video? So this is really important data, or really cool data to get. It's like how many things are in there, and also where they are in relation to each other or other objects on the screen. Instant segmentation. So just like object detection, instant segmentation can classify and localize where an object is, but it can actually understand more. So here, right, you can see this is really small, but it's drawing a box. You might not be able to see it too much. It is drawing that kind of rectangle around where it is, but it's also drawing, just like the trucks, very specifically where it thinks, in this case, it's a bottle and water. So it's actually drawing pixel-wise where the bottle is and where the water is. And then from here, you can do a volumetric calculation to understand like how full the bottle is, right? Like how many pixels are overlapped by water in this case. And you can say, well, the bottle is like, you know, 60% full. And then when it's here, oh, cool, it's almost like overlapped all the way. And then it's going to get to like 90 and 100% full. Another good example would be like, if you need the precision of knowing if not just like a whole hand touches something, but a specific finger. So one application is if you've used VR headsets and they're trying to make it better for you to type on keyboards in VR headsets, you would actually want to understand precisely where like fingers are and where a key is, not just where whole hands are drawing a box around it. You'd want pixel-wise, where is something in relation to another object, and then is it interacting with it or not? So you could look at fingers, and then look at keys on a virtual keyboard and see when a finger presses it and then count it as pressed. So if you need more precision, instant segmentation is kind of the way to go. And also turns out sometimes if you're training, even if you just care about object detection, training something on instant segmentation can be more accurate sometimes than training just for object detection solely. Feature point clustering. So someone talked about facial emotion applications, and the feature point clustering is really good for that, where you do pose estimation. In this case, it's doing body poses and actually does predictions of like when they change poses in yoga. But you also use the same type of labeling for facial features. So there's a common, I forget how many it is. It's something like 46 points or something like that on faces, where you measure where eyes are, mouth, nose, eyebrows, and then from that you can actually map those feature points, and depending on what kind of faces people are making, you can actually get a prediction of what their mood is, or how they're feeling. Image captioning, so you can actually understand the context of an image a bit. There's a way of combining, I think someone had mentioned like long short-term memory, so like an RNN with a CNN, and actually have contextual understanding of an image versus just classifying like beach and kid and kite. You could actually do something like, hey, there's a child on the beach flying a kite, so it actually has some understanding of what's going on. Generative deep learning is really cool. There's something called a GAN, generative adversarial networks, and you can generate like original designs and pictures with it. I'll link to a couple things here if you want to check these out. This Medium article goes way more into GANs. So I've actually done a lot of GAN work. I was working with someone, actually this link kind of shows a project I was working on. I was working with someone to essentially generate original housing designs. So he used to be an architect, and one thing they had, like a problem they had, is someone had to draw a whole bunch of like exterior designs before they'd even get into more design. And so we programmed a GAN to do that for us, and we took data from a whole bunch of like famous architects and then generated designs based on that. It was really cool. And so this little image here on the right is actually from that GAN, but you can tell it doesn't look anything like buildings yet, but this was like an in-between stage where it just generated really cool looking art. And I really liked the way it looked. So if you're interested in making art or something, you could totally do that with GANs. Choosing a model. So there could be a lot of different factors that actually go into choosing a model and how to tie them together. But when you're first just getting started, you can think about what what is the problem you're trying to solve and what's the outcome you're looking for? So are you trying to just get object detection, like counting how many things or roughly where they are? Do you need instant segmentation, like much more precision? Or do you need feature points like pose estimation? So this is a really good place to start. If you haven't, trained your model yet or started labeling a data set, you should be like, all right, what do I need from this model? And then go from there. So here's a little demo again. You can see this is a little mouse. And when it's interacting with the piece of food, it's classified as feeding. And when it's not interacting with it, it's not feeding. So again, that's a kind of a cool demo of seeing like relationships between an object versus another object in a video. All right, so actually, does anyone have, out of all these different ones you saw, which ones do you find the most interesting? Or if there was another workshop on one of these, what would you want to see this on? Besides object detection, because that's where you are right now, at an object detection workshop. Someone said GAN. GANs are super interesting. I think that would be really, really fun workshop. You could come away with a GAN, like trained yourself, which would be awesome. Someone said combining multiple images and videos. What do you mean by that? Like combining, that occur at the same time? So you mean like if you had two video streams looking in different areas, but then combining them together to create like a longer, bigger video that you could do like tracking in or something, or object detection in? Yeah, so I've seen that with security stuff. So there is ways of doing that. So you can combine multiple videos and then track like across different, like you can even do tracking across different video streams, which is pretty cool. So it said instant segmentation, generative deep learning, cool. Oh, definitely, I'm gonna definitely do one on instant segmentation soon. So keep an eye out for that, probably in the next month or so. All right. So object detection in a gist. So we're going to get to labeling really soon and then coding, but just want to give you a couple more ideas of what we're doing. So object detection does vary depending on what architecture you use. And I'm going to link to this article here if you want to get more details on that. But essentially what you do is you find proposed regions where it's like, hey, I think something's in here. I'm detecting some sort of foreground, out of a background. Then you run a trained classifier over it. And then you calculate an estimation of object location. So, this is like, cool, something's over here. We run a classifier, pretty confident a goose is here, and then we'll draw a estimate of where we think it is. And I share more links later. So if you are curious about any specific architectures in the coding notebook, I have a whole bunch of links. So popular object detection methods, we have single shot multi-box detection, or abbreviated to SSD. It does object detection and it does it really fast. This is really good on lighter weight hardware, actually. So if you're doing something on like a Pi or something that's not like a full-blown desktop computer with a GPU, you can choose this and it tends to have pretty good frame rate results. And you have you only look once, or abbreviated to YOLO. It does object detection. It is also pretty fast, and there's several iterations, and a new one just came out not too long ago. And I actually don't remember what the benchmarks are. So I'm not sure at this point if it's lighter weight or not than SSD. I don't think so, but I could be wrong. You can look it up. And then we have a mask RCNN, or a faster mask RCNN. It can do object detection and image segmentation or instant segmentation. And it tends to do this with a high accuracy, but it's slower than these other options. So again, when you're choosing things like model architectures, there's often trade-offs. And that trade-off is often like, does it run slower or take more computational resources versus, how fast can it run, and the accuracy, sorry. And then today we're going to use something called Detectron 2, and it's actually a fork of a faster mask RCNN. Let me give you a little preview of what it can do. And the cool thing is it makes it really easy to do all these things. So we'll label a data set. It's kind of another layer on top of PyTorch, which is a popular deep learning framework. So you can see here it's doing object detection. It's saying, hey, this is a plant, this is a bottle, here's a laptop. We'll let it run. Doing object detection here again. And then here it's doing feature points. And then here it's doing a cool, unique thing to that they have called dense pose. So I think it gets it from feature points, but then it's actually kind of drawing a 3D model of where it thinks the people are. And you can see it's not 100% perfect, but this is really cool. I've seen people use stuff like this to generate 3D characters in games or videos. Because you can actually get rid of the real video and then just have these 3D models interact with each other. And then it goes here, and then we'll see it does instant segmentation, right? So it's drawing specifically where something is. Like this is a table. These are the cups on the tables. Again, it's drawing those pixels, not just a box around it. And then here, you can see it switches to this view where it's actually doing, I always blank on what this is called. I think it's panoptic segmentation. It could be wrong, but essentially what it's doing is it's drawing every single pixel. Like it's making a prediction on every single pixel in the image. So here you can see it's doing the background as well as the objects in the front. So we have like the bowl and cup, the table like before, but also what is this background? Is it a cabinet, a wall tile? If it was outside, it would make a prediction on like the sky or I think cityscapes, which is kind of cool. So this can be useful if you need more context for like, let's say you're doing something with robotics and you want to understand what is the background you're looking at. Using something like this can be useful. So that's what we're going to use today. It's really, really cool. I really like it. All right, so just to mention, so we're going to cover data annotation and machine learning part of computer vision today, but there's a lot more to it. So if you're thinking about doing this as like a professional project, or if you are working at a job and you're here to learn about computer vision to do it, for your company, there's just some other steps to think about. You have device management. So someone had mentioned edge computing earlier as well. So you have to manage the actual computational resources to do like running the computer vision models on, as well as managing the sensors. So in this case, cameras. But a lot of times, like if you're doing other types of machine learning, you might be managing other types of sensors. And then you have data collection. So if you're managing cameras, all those frames are coming in from somewhere. You need to collect those and like have them in one centralized space, or if you're not doing it from cameras live or anything, then you need to create data sets with something like web scraping or collecting those data somehow. So I actually worked on a project with like deers, and there were, people had like trap cameras up and stuff like that and got pictures from that. And then we're going to cover data annotation, labeling, machine learning, the model selection and training. And then once you do that, then you want your model to run somewhere. So in order to run a model in the world, it has to be deployed, right? Like once you have a trained model, cool, how do I use it? So again, that's usually a combination of managing computational resources and then managing the model and then managing some sort of input. So again, in this case, maybe it's cameras or an image. And then often, if you're doing machine learning, you want to have something kind of like repeat all these things. So it's called a continuous machine learning. And the reason for that is you can kind of avoid something called model drift, which is like an example I always use is, say we're doing an Amazon Go, like the store grocery thing, right? And you were detecting people walking into a space. If you trained your data on people walking into the space in winter, chances are they're wearing coats, they're wearing big hats and beanies, maybe their hoods are on, they have giant boots. And then you're running your model, the same model that was trained on all that data, and then you're looking at people in the summer and they're wearing like tank tops and shorts, they don't have any hats on, they look a lot different than they did in the winter. So a lot of times, if you have a deployed model, especially with computer vision, and there's going to be seasonal variations and things like that, you kind of want to keep collecting the data and then keep training your model, and it's going to either get better or remain good over time. So this is kind of the full computer vision life cycle and all these steps. And not to be super salesy or anything, but we do offer like model building and custom managed labeling, custom model building, and other machine learning solutions. And also we're building a platform to do all these steps in one platform. So it's actually kind of annoying and hard to go back and forth between a whole bunch of services that do different parts of these things. So we have a really cool platform we're building out. You'll see part of it today for the annotation, but you'll be able to kind of plug and play across all these different aspects, which will be cool. So if you do want to see a demo of that, or you think your business could use it, you can fill out the contact form and we can give you a demo, because it's not completely open just for anyone to sign up for yet. All right, so we're going to get to image labeling. I'll share this link again. This is where you can just sign up for free, the free trial. We're changing pricing soon. So I think the trial will be longer, or the time period might be going away soon. But I don't have a timeline of when that's exactly happening. But there's no card or anything to sign up. So you can literally just go in, put your email in and sign up. And then you get a verified email, and then you'll be able to open up the labeling tool. So I'm going to exit out of the slides. Oh, and if you do want to follow along, I'm going to be using just some example images here showing different ways of doing labeling. So we'll do it for object detection. I will show you how to do instance segmentation as well, because it's actually pretty similar. And I'll bring up where you can change something in the code as we're doing the code portion to also train on instance segmentation. So hopefully, if you're okay fiddling around a little bit after the workshop, if that's actually what you want to do on your model, you'll be able to do that hopefully pretty easily. All right, so hopefully you're signed up. If you want to do some labeling, totally encourage you to do that. And even if you don't follow along with the labeling for this workshop, you'll have all the knowledge of how to do this after the workshop on your own data set. So that's really the point here. We're not going to go label hundreds of images from scratch, but I do want to show you how to do it. So you'll be able to take this and then work on your own project. So here we're in the data labeling tool. You can see all these other things are grayed out. That's what's coming soon. All those other steps I talked about, like training models, managing cameras, looking at detections and stuff, that's all coming soon. But here you'll have a screen that looks like this without any projects. You want to hit new data set. I'm just going to call this, call it workshop. You'd want to have a meaningful name. So if you're doing like geese, you would say, geese object detection or something like that. I'm going to hit save and continue. I'm going to hit add sources. And then for this, I'm just going to upload local images that are already on my computer. But you can also connect to Amazon S3 or Google Cloud Storage. So most people probably store their data in one of those things, at least in a corporate setting, maybe not for experimentation. But if you're collecting like thousands of images, chances are it's in one of these things. So you can easily import those in by kind of providing the source path and any credentials if you have it locked. So I'm going to choose my images. And I have a data set here. So I'm going to show, again, it's going to be several different types of examples, just so hopefully one of those types will work on your data set that you want to do, train your own model on. So it's going to upload. This might take a second because my Wi-Fi isn't the best. Also, I didn't resize these images, so I think they're all like high definition or something like that. If these were at a more reasonable size, it would upload faster as well. So now I'm going to go to label definitions. And this is where we create our labels. And it's good to know at this point what you want to do. So we talked about like instance segmentation, object detection. How do you want to label your images? That's good to know at this point. So I'm going to make several examples just to show you how to do it. So I'm going to say goose. I'm going to have a rectangle for object detections. And then this color is just for you as the labeler. If for example, your geese might be on a green background and you want your labels to pop out more, then you want a color that's probably not green. So I'll have that blue. I'll hit save. And then I'm going to show you how to do the instant segmentation. So I'm going to make one called Goose Polygon. Label type here, I'm going to select polygon, but you can also see we do like classification, feature points, different types of labeling in here. I'll select polygon. I'll leave that color. I'm going to hit save. And then I'm going to show an example with cars that's also polygons. I tend to do a lot of polygon labeling in computer vision work because you can kind of just do it for object detection if you wanted to afterwards. But if you want to train more accurate models, often you need a polygon mask. So then I'm also going to make one for a cup. You'll see why. And then I'm going to make one for PCBs, printed circuit boards, like for manufacturing. I'll do polygons again here. I'm going to do a different color just so it stands out more. I'll hit save. And then I'm going to do one for PCB damage. So this would be like we're labeling damage in a quality assurance line. Polygon, save. All right. Now I'm going to scroll down. You have options for adding instructions. If you're just doing your own personal project, you might not want to do this, but if you're working with a labeling team, it's really important to have clear instructions of how to label something. So you can even embed images here as well. So if you wanted to have a good example of a label versus a bad example, like for example, even if I was doing the labeling, I'm not a domain level expert in a lot of stuff. Like if I was doing medical images, I would want a doctor to tell me, this is the tumor type we're looking for. This is how to label it. Here's some examples that might be close looking, but they're not that type. So don't label those things. You'd want to document all that here so you don't get confused or your team doesn't get confused. But we'll just leave it blank for now. And I'm going to hit save and start labeling. This will bring up our labeler tool. You can also navigate around to here. So if you want to add more sources, you can go back to sources. By default, it'll show all the pending images to be labeled. But if you label them all and you load your tool and you're like, why is it blank? You can come back here and look at all submitted or all images or anything like that. And this will drop down. All right, to label for object detection. So this is like actually how I labeled the geese that we're going to use for our object detector, right? I'm going to take this rectangle label, and then for object detection, I'll just draw a bounding box or a rectangle around each object. So here, doing it for geese, you want to be typically as close as you can to the goose without actually going in. So I think I went a little bit in on this beak. So I'm going to hit escape, adjust this a tiny bit. So you can always come back, adjust them. You can move them. So if you just want to move the whole box, you can do that as well. And then from there, I would just hit submit. And then I would do that for all of my images. So I had like 119 images of geese, and I want to label every single instance of the goose. That's very important because if we had another goose in this image, or let's delete one label, if I just did this and I fed it to my neural network, it'd be so confused of what it's trying to learn, because I'd say, hey, learn this, learn to detect this object. And it would look at that and be like, cool, you're looking for this. And then it would look at the image, make a prediction or something like that, and be like, oh, like this isn't what you're looking for because it doesn't have the label. So it's really important to label all instances when you're doing something like object detection or instance segmentation. The only reason like why you wouldn't is if you had a goose really far away, like let's say there's one way back here, and we were okay if our model didn't predict it, then maybe it's okay not to label it in that case. But if we had one pretty similar looking, right, then we'd want to label it. Otherwise, our model will get really confused. All right, and so that's how you do object detection, just bounding box labeling. Let's show you polygons. So I have this goose polygon label, and you might have seen something like this if you're doing polygon labeling or mask labeling, where you want to draw. I'm going to do a very quick, terrible job right now. But if you want to do polygons, you basically have to just trace around the object you want to detect. And it takes a lot longer than doing those bounding boxes, right? Has anyone ever had to do this before, like for their job or just a hobby project? Because I know I have, and it's so time consuming. Like I'm doing a pretty terrible job here, right? But this took me so much longer than bounding boxes. So whenever possible, it was actually kind of dumb, but it'd be like a reason to do bounding boxes sometimes is because it was so much faster. So that's connecting a polygon, and then you can come in and adjust things. But let me show you a really cool feature that makes labeling polygons way faster. I'll delete this label. I'll select this goose polygon again, but I'm going to enable something called Smart Poly with this little button here. And now you get that crosshair for drawing a bounding box. And let's draw a bounding box very closely around our goose again. Hit just click, and then you can see it snapped a polygon and traced around it. So that's so much quicker than manually drawing those things. So let's do it again here. All right. And again, you want to be very close to the object. If you're way too far away from, like way out here, it won't do as good of a job, or it might even mess up altogether. So I'm going to click there, and you can see it did a pretty good job here, but it's not perfect. So you can come in and adjust these things. So there's really two nodes I needed to drag there. So if that still like gets me 80 or 90% of the way there labeling, then that's awesome. I mean, even my eyes, like I have a hard time telling where this goose ends and where the sidewalk begins, right? And this is a model trained to just generalize on objects. So this did a pretty good job, but we can go and adjust it if it does make a mistake. So hopefully you see like the difference of labeling for object detection and polygons and why one is so much faster. But there are really cool tools now, like the Smart Polygon tool, that allow you to label polygons way faster. Did anyone think that was cool? You can let me know in the chat. Are you more excited about labeling now, data labeling? I'll show another really cool feature. So this is actually how I would go labeling these now, right? So if I need to do bounding box around my geese, I'm going to select this other thing. So there's this other little menu here. You get this drop down. I'll talk about some of these in a second, but I am going to turn on something called auto label. And we actually had part of this when we were setting up our classes. You might have seen it. I forgot to mention it, but we can also set up here. So I want to automatically have a model try to find all the geese. So we have 81 pre-trained classes that you can select from in here. Unfortunately, there isn't a goose model, but there is one for birds. So I'm going to select bird, and then I'm just going to hit OK. So this is me turning on auto label. And you can see, cool, it found both of the geese in this case. And I'm going to hit submit. This will go to another frame with geese. And auto label is still turned on. And usually it's much faster. Of course, doing a live demo, you know. Come on. I'm not sure why. I feel like something went wrong there. We should just apply. You saw it apply on the first frame, and then it applies to the next frame. But if for whatever reason, if it doesn't apply to the next frame anyway, then you can always just switch back to the manual labeling. But I did this like auto label with a lot of my geese frames, and it was awesome because it would just detect all these birds and automatically apply a label to it, which is awesome. So again, it's like really about time saving. Any features for data annotations really about time saving because it takes so long, especially if you're doing something like polygons, or even like in this case, I've done data labeling for manufacturing situations. And a lot of times there's a lot of product on conveyor belts. So if there's like 40 things in each frame, if you're doing these bounding boxes, it takes forever. So let's go on. Let's try auto label again in here. So we have a couple frames of cars. I'm going to turn on auto label again, and then let's look. I know there's one for cars, and let's go ahead. We can also add trucks in here. So in our case, we're going to say like cars and trucks are the same, and we just want to label them. And it's a polygon label. I'll hit OK. It's applying the label. Boom! You can see it drew a car, or labeled the car kind of automatically. So now let's hit submit. Go to the next frame, and you can see. This is what it should have done in the goose. For some reason, it hung up there. If we refresh, it probably would have worked again. So this is just automatically finding all the cars in the images. So it's saves so much time if you're doing like video frames like this. We will see some new cars that kind of come in a second. But it's essentially just following that car, automatically applying a label to it. And then you can see it actually kind of made a mistake here. So it labeled these two cars, but it did miss this car. And the reason why, like, even if you're using a model to label your data, you want to look at it is because of stuff like this. Like there's no perfect computer vision model, right, for almost anything. And so what we're trying to do is get to a point where we can have models do most of the work for you, but you still want to QA it and make sure that the data is correct and being labeled properly. So, you know, in this case, it messed up. I'm going to turn on Smart Poly, click that car label, and then I'll just label it again myself. So occasionally you have to still do these manual labels. Smart Poly makes it way easier if you are doing instant segmentation. And I'll just hit submit and let's keep going. And then it got it in this frame just for some reason at the other angle, it didn't make that prediction with auto label. So you can see like going from having to draw all these, even though they're fairly simple shapes, like way easier than a goose. If we had to do that on every single frame with like 3 cars, that would take me so much time versus automatically applying those labels. And a cool thing that's coming really soon to auto label is being able to tie your own computer vision model in. So imagine you're working on a complex data type that we don't have a pre-trained class for. It's very specific to your use case. So if you're manufacturing some sort of product and you're making something that we don't have a pre-trained model for, you'll be able to label, I don't know how many it would take depending on what your data looks like. Let's say it was like several hundred images with your data in it, and then train a model and then tie that model into auto label and then make those predictions automatically. So even if you're doing really complex data, soon you'll be able to use something like auto label on it, which is going to be awesome and save an insane amount of time labeling. So I'll hit submit here. One other feature I'm just going to show, and this can be really useful if you are ingesting video frames and then you're labeling like frame to frame. So I'm going to use Smart Poly again. I'm going to label this cup, because why would I draw polygons manually when I can have computer vision models do it for me? Oh, that got the shadow a little bit. So if you aren't perfect with it, it can still make a little bit of mistakes, but you can just go in and adjust it. One cool thing too that I didn't talk about, so if you need to add more nodes, you can do that by clicking here. And if you wanted to delete a node, you can select it and then hit backspace or delete. And then so it's very easy to fix mistakes like that. So again, if it gets you like 80 or 90% of the way there, it makes labeling much more fun. And boom, that worked really good. So now I'm going to enable a feature called track forward. And what this is going to do, this isn't auto labeling like before where it was just finding every instances of it. This is actually doing something called object tracking. So we label these objects. It's going to go to the next frame of the video, try to find those same objects that we labeled automatically, and then apply labels to them, even though they're at different angles and stuff. So it works usually pretty good from like frame to frame, and the objects aren't moving like a ton, right? Like if you're a person walking by or a car driving by, it would automatically found out like that, oh, you moved, cool, let me automatically label you again. So I'll hit submit with track forward enabled, and it can take a second to load. Boom, different angle, right? Just from a video. And we'll do it again, just on a couple more frames. And again, if it isn't perfect, you can go in and adjust those polygons. So it will just depend on how complex your data is and how much moving and stuff is happening. Let me see, I know there's a question in the chat. Also, if you have any questions, please put them in. We're almost done with the labeling portion before the code. So if you have any questions about labeling, I'd love to hear them and we could tackle them right now. David said, can you remove the inside of the handle? Inside of the handle? Oh, so like, I think you were saying, again, if you want to go like at all of your images, you can hit this little drop down. I'll do that. I should have saved that, but I didn't. I think I know what you're talking about, David. So if I go back one image and oops, let me refresh this. You're talking about like a hole, right? If I wanted to have a label around the cup, but then have a donut. Like if you're labeling a donut, you want to label the donut, but not the hole. That's typically called like an occlusion in labeling. We don't have that feature built in here yet. I know some people ask for it. Have you had a use case where that's been really prevalent? Like I know, I'm sure there's use cases for it and stuff, but a lot of times we find that just labeling without the occlusion does really well. But I know what you're talking about. That would be like having a label and then being like, this isn't part of the object. I know there are ways, like we have tied occasionally things together too. So let me take this cup polygon and let me label this again. So there are kind of like, ways of, oops, I did not do a good job of being close to the cup there. That's kind of my fault. But you might be able to do something like take another polygon, draw around that area, and then kind of associate them. But we don't have a way of automatically associate those labels in there. Let me just go into this one other example. So we have this PCB board. Let's say we want to label the PCB to detect it and then, detect it for damage. So we could just label this. Sorry, get selected. Again, I'm using polygons here. Maybe you use the square for object detection, but maybe you also want to detect, when the PCB is at a specific angle or anything like that. And then I would want to label that PCB damage. You'd also turn these off just like visually if you don't want to view them as well. I'll label by toggling this I, so it can be a little easier. And then I would just, draw around these scratches. Boom. Then I would just hit submit. And once all of your images are labeled, then you have this review tab. If you're working with a team, you can also do like approval. If you want to manually look and make sure that someone labeled these correctly, you can totally do that. Then you can hit export. If you don't want to do the manual approval, which is really important usually for a lot of corporate settings, but if you're just working on a hobby project or something yourself, you can hit submitted annotations here, and that will just be like, hey, you went through, you submitted them, you trust them, now you're ready to download them. And then you could export it in Cocoa. This is what we're going to import in. We're going to use a Cocoa dataset, import into Python. Cocoa is a really popular format, and a lot of deep learning frameworks have functions that can automatically parse this data. So I like using Cocoa a lot, but I also use our own JSON version quite a bit. But if you need Pascal VOC or YOLO, depending on your application, those are in here as well as Create ML, which is Apple's version. And then you have some options for train, test, split, and validation. I'll talk more about these when we get to the coding section of actually training our model. But typically when you're training something in deep learning, you want to have 3 data sets. One is for learning or having your model learn. One is for validating your model as it's learning. And then another one is to test it after you're kind of done with the whole training process. So I'll talk more about that in a bit. I'm going to hit export. It says my export has completed. So once you do that, you'll get an email with a download button. You also get a notification here. Occasionally, I've noticed that it takes a few seconds to show up, but if that's the case, you can always hit refresh, and then you should get your push notification. So there it says, 14 seconds ago, I'm going to download my export, and then you see you just get a zip file, and this is what we'll want to take the contents of the zip file and then upload it into Google Colab and do some training on it. If we look at this JSON file, it's just going to look really crazy here. All it is just mapping out those annotations we did and then relating them back to an image path. So you can see this is just a whole bunch of numbers. These are just like those bounding boxes we drew, saying, hey, they drew a rectangle here or a polygon here. And then they map it back to a specific image path. So that's just how the model will read in data and learn from it. So let me know if you have any questions before we move on to the code, and I will get to them. So any questions on data labeling or this tool in general? Someone said, how do you manually select an object? Do you mean like label an object, like manually label an object in case you just came in? Or do you have a different, like what do you mean by select, Adam? Oh, and also said, where's the export button? So the export button is in review. So once you label all your images, you'll get sent here, but also you can click this review tab if you want to export before you label everything. And then just click export dataset, and then you get all those options I just talked about. You said, how do you manually select an object? So I'm not sure if you just came in a little bit late, potentially. You can do all the manual labeling like you would on any other tool. So you could select, do the rectangles for object detection, or you can manually do a polygon. You just select it and you just don't turn on Smart Poly, and you can do all the drawing you want. Right, so if you have really, really complex data type and like Smart Poly or something just isn't working on it, you can always come in and manually do all this. Again, I'm doing a terrible job here. Wouldn't actually use this as a label, but you go around your object, then you connect the 2 nodes at the end. Hopefully that answers your question on manually selecting. I'm not sure. David said, do we upload the zipped? It depends on how you want to do things. You don't have to worry about it for the workshop. We'll actually use a different zip file or a different file. Yeah, so don't worry about it, David, for now. I usually upload it to Google Drive unzipped, but you could upload it zipped and then unzip it using a Linux command. I'll talk about that in a second when we get to the code. So it's up to you. I usually already unzip it and then I just upload it to Google Drive, and it just makes it easier to work with consistently as a data set. And you'll see why, because Google Colab is kind of a temporary Ubuntu instance, and you can do a lot of cool stuff with it, but it's nice to just have persistent data saved in Google Drive. But I'll talk about it, but don't worry about it for the workshop. Anybody have any other data labeling questions, or were there any features you thought was really cool? Or anything you learned about data labeling you thought was really cool that you've never seen before? And again, I'll share the link if you want to sign up, is there. And I'd love to hear your feedback. So if you use this on your own data set, I'd love to hear about it. Like, is it working awesome? Was there something we can improve? Let me know. And then you can let me know on LinkedIn or the Slack channel is a good place for that. But any other questions on labeling? Or like I said, anything you thought was really cool or that you're excited about? I love the Smart Polygon tool. Again, I don't know if you've ever had to spend time labeling a data set before with polygons, but having something like this that can just do a really good job for you is a game changer. It saves so much time. I love it so much. I can't imagine like not using this anymore. I never want to go back. And then same with like the auto label is really crazy too, because like if you have a object that it works really, really well with, like out of those 81 different classes, like the birds, that's crazy too, because instead of labeling every single goose for every photo, you just turn that on and you just kind of QA each image to make sure it's doing a good enough job. And if it misses one, you do it yourself. Like occasionally they're kind of blended into rocks or something and it didn't see it. But that also just saves an insane amount of time. So instead of me spending an hour or two labeling even a smallish data set, now it's like half the time or something. It's really crazy. Cool. So are we ready to go on to coding then? Let me see. The sign up does not work. It says you must agree. There should be a terms and service. Let me open up that link. Does anyone have a problem signing up? You should check this box here at the bottom, and then you should be good to go. And you'll get a verification email, and then you can use it. So hopefully you saw, that's kind of all the stuff you'll need to know about doing it for object detection or instance segmentation. And then if you do have any questions or any other problems, again, just let me know. What was I going to say? All right. I think I don't see any other questions, so let's go on to the coding section. All right, right before we jump into the code. Oh yeah, so I was gonna follow up with that because I saw you ask, will I share the workshop recording? Yeah, so I'll share it out in an email to everyone who RSVP'd. You'll get an email with the recording later. Also, it's on our YouTube channel, so if you want, let me find the link for that. Actually, this is on our YouTube channel. Yeah, let me get you a link real quick in case you want to follow or look for it later. So here's the link. It'll be uploaded here for anyone who wants to subscribe and get notified for it. I'll probably upload it tomorrow at some point. All right, so a couple libraries just to talk about before we get to the code part. There are so many you can use in computer vision, but some really popular ones are PyTorch. It's a library from Facebook for machine learning and deep learning. Same with TensorFlow and Keras. It's kind of like similar to PyTorch. You'll see people use either or most of the time. It's just kind of a little bit different, and it's made and maintained by Google. And then we have OpenCV. It's really awesome for processing images and doing cool stuff with computer vision. It has some built-in deep learning stuff. I don't use that stuff too much, but I do use it a lot for processing images before I bring it into deep learning models or after I have a model do something. They have NumPy. It's great at processing multi-dimensional arrays, which is actually what images become when you import them into code most of the time. And they have Pill and Pillow. It's another image processing library. All right, so I'm going to give you this link in the chat here and open it up if you want to follow along. We're going to get to the coding part. And if you've never done deep learning before, or if you've never done computer vision, you're going to train your first model. And if you have done it before, you'll be training another model, and hopefully it'll be really fun and really cool. And you actually come away with one, hopefully cool knowledge that you can apply to a model that you have in real life that you want to build. But also, like, you'll get a cool visual output of a video, right? Like running a model on a video and actually doing object detection. So it's really cool to share out, on social media and stuff. Be like, look, I did computer vision. People love seeing visuals of computer vision models. It's awesome. All right, so I shared the link in the chat. If you're following along, just if someone wants to let me know they got here, that's cool. And then you want to go to File and save a copy in Drive. So this will create your own version of this. You can bookmark this original link if you want to always come back to. So if you do mess up your own copy, because you'll be able to edit anything in there once you make your own copy, then you'll be able to run all the code as well. So go here, go to that link in the chat. I'll give everyone a minute, and then hit save a copy in Drive. And then if one person just wants to let me know that worked, that'd be great. Someone said worked. Awesome. Cool. Someone said, is there a choice other than Google Drive? Drive is blocked in your work computer. I don't know if there's a great option for you right now. Like, you could totally do all this stuff locally. I don't have the material, I think, prepared to download it. And if you did it that way that I can think of, you'd have to, like, there's other versions where you could probably host a Jupyter notebook, which is essentially what's happening on here. But I don't have another option available right now. But yeah, like, you can go you can go download this or host it on something else. But I don't think I have that prepared to send you a link to it. But that's a great note. And maybe I'll have to do that next time in case someone else has the same issue. Sorry. All right, so this is Google Colab. This is a way of Google. This is a way of kind of hosting a Jupyter Notebook on Google. A Jupyter Notebook is a really popular tool used in data science and machine learning. If you've never used it, it's a really cool kind of way of writing code, documentation, and visuals all in one place. So it's really great for running like experiments and exploring data and seeing visuals. It's really awesome. So go to File, save a copy in Drive. You'll have your own copy of this. If you want to edit anything here, you can actually double click in. You can see now we're in this like text edit option. To get out of this, you can hit Shift Enter. And then just to note, so you don't need to do anything right now on this, but I do want to note that if you are creating your own Google Colab and you're doing deep learning, you can select a different accelerator here. So by default, it's none. Since you made a copy of mine, it's already selected to a GPU. And most of the time you need a GPU or a TPU, tensor processing unit, to run deep learning models pretty quickly. So if you ever do your own, you can do that here. And that's why a reason why Colab is so awesome is it gives you access to GPU for, I think it's like 12 hours a day or something like that, for free. So it's a great way to get started with deep learning and computer vision if you don't even have hardware for it. So code cells, here is some Python code. It's just going to print out hello world. So go ahead and run this. You can hit this little play button. That's going to run a code cell. You can also hit Shift Enter when a code cell is highlighted. So if I'm going through this and you don't see me hitting the play button, it's because I hit Shift Enter. You can see it said hello world. So if you've never done any Python before, now you have. You know how to print something out to the console, or in this case, the notebook, saying hello world. And it might take a second to run it as it creates an instance for you. Once you do that, everything should run much quicker. So just someone let me know, were you able to print out hello world? And hopefully we'll have no problems. Awesome. Someone said, yep. And then just a quick note. So you can run terminal or bash commands. It's totally okay if you don't know what these are. But often if you're using like a Linux system, you can do stuff like you type ls and it'll say, what's in that directory. So to do those, you hit the exclamation point at the beginning, and then you would type out that command. So it actually gives you kind of a whole little mini Ubuntu instance, not just a Jupyter notebook, which is really cool. So we can do that. Let's go ahead and start setting up our dependencies. So we're going to install PyTorch 1.8.1. And actually, I didn't mention this. So Google Colab has a lot of packages already pre-installed. So it has like PyTorch and TensorFlow and a whole bunch of common packages pre-installed that you don't have to download. The reason why I keep this code cell here is it also automatically updates those packages. So if PyTorch 1.9 comes out, it'll probably put it in here pretty shortly after it comes out. And then some of this code might not work. So I have this here just to check that, if 1.8.1 isn't in here, it'll uninstall the new version and put it in here just to make sure that it's going to continue to work. Let's go ahead and install PyYAML and PyCoco tools, some other dependencies we're going to use. We're also going to import PyTorch and Torch Vision. Boom, cool. This is just to double check what are those versions. Anytime you're programming, it's important to have the correct versions of anything, otherwise stuff might not work. So here, I'm just printing those out again, just for a sanity check to make sure that I have PyTorch 1.8 or some version of it to work with this Detectron 2 version. So here we're going to install Detectron 2, pip install Detectron 2. First, again, we're verifying we even have a little assert statement, making sure that PyTorch starts with 1.8. This might take a second, but most of the requirements are already satisfied in here, so it shouldn't be too long. And then we're going to pip install this version of Pillow. I think I had some problems with the newer version. Maybe that's fixed now. I should double check, but I know this one works. Don't worry about any of these warnings. It will say like you need to restart the runtime for it to be in there, but it's actually fine. So don't worry about that type of warning here. And then here we're going to import the stuff we're going to use. So again, if you haven't used a lot of Python, this is like we downloaded libraries. Now we're importing them into our project so we can use them. So we have Detectron 2, various things from Detectron 2 that we're going to use. You'll see as we go, and some other libraries like NumPy, and CV2 is OpenCV. It's called CV2 when you import it in. All right, so we already created a data set. You saw how to do everything in here, but the links are here too. If you want to go read the docs or connect on Slack or anything, please join in there and let me know if you have any other questions. And then here, we're going to download a data set. So I'll talk about a couple different ways of bringing your data set into Google Colab, but I'm just going to use this for our workshop because it makes it much easier. I have the Goose data set that's already labeled, stored on GitHub. So we're just going to git clone it. It's going to download it. And then we do that ls command, the listing directory. We can see that now there's an image folder inside that Goose object detection dataset folder, and then also all the JSON files we'd expect from our train validation split labeling. You can see all of our image paths. All right, so now we want to import this dataset into our Python code or Detectron 2. So they make it really easy. They have a function called register Coco instances. That's what I'm saying. Coco is a popular format, and a lot of frameworks have the ability of automatically knowing how to read it in. So it's really cool. So we're going to use that here. So I'll go ahead and run this code cell. And then now let me talk about how I would bring in a data set in a different way. So if you're labeling your own data set, one, you can store it on something like GitHub and download it, depending on if you want to do that or how big it is, because GitHub's not really made for that. So if it's a small data set, that's cool. But if you have a really large one, it probably won't store it on there, as well as maybe you just want to store it in different fashions or whatever. So there's a couple different ways of doing this. You can hit this little folder icon here, and I'll bring up the directory of what's going on in this Colab notebook. You can see this is where we downloaded our folder. So one, you could unzip that file that we had, and then just drag these items up into here, and they'll upload. But the problem with that is that, it's not persistent. So if you were to go away from this Colab notebook and come back later, you'd have to upload that data set again. So it'd probably be fine for the size of this data set. It's not very big. But if you're working with hundreds of images or sorry, maybe like thousands of images that would take a long time to upload every time and be really annoying, you don't want to do that. So it's much easier if you just save a copy in your Google Drive somewhere, and then you can hit this little mount to drive. And this one, because it's on mine, I don't think I have to do the extra step right now, but it'll pop up a code cell on yours and kind of walk you through how to mount to your Google Drive. It'll like have you paste a security code in or something like that. But once you do that, you can now navigate your Google Drive folder, and you can make like a machine learning folder or a dataset folder, store your stuff here. Let me go grab an example one. So here I was working on like a candy demo, like using it to detect some candy. And maybe that's not a good one. Here's one with a dog that I was doing. So here's like the train test validation JSON. What I'd want to do is just navigate in here to wherever I save my data set on Google Drive. And then I would come in here and I would just hit copy path. And you want to change out these paths. So if I was doing this on this dog data set instead of the goose data set, I would just paste in here. And you can see it says content, drive, my drive, that's the Google Drive part. Then it says like wherever you store that file. And then this is an important part. So this first part looks for the JSON. So you can see this is training, this is validation, this is test. These are the variable names they're going to become that we can call them later. And then this part points to where the images are. But one caveat is that the path inside your JSON file, if you were to look at it, already has the /image appended on it because it knows there's a /img folder that was exported with it. So you'd actually like, it's tempting to be like, cool, here's all my images. I'm going to copy this path and put it in. But you actually just want to remove this /image at the end. So you would do that because it already knows to look for a /img. So just go to the folder one up where your images are stored, and it should be good to find it. And it might sound really complicated, but once you do it once, it's actually really easy and not that hard. And it's probably the best way of just storing your data set on Google Drive and then easily bringing it into Google Colab, if that's how you want to do it. So I know if like, you might not all have GPUs at home to train. You could also set up Detectron 2 or TensorFlow or anything like that on your local machine and then have a data set downloaded. But I just want to mention how to bring your own data set into Google Drive, because a lot of people will use Colab for like a school project or even just like a proof of concept. It's a pretty great place to do experiments on. And that's how you bring your data set in. All right, so if you ran this, we now have our 3 data sets. And then you can run this code cell. This is just getting some data from our training data set, namely the classes. The metadata catalog is getting things like the class name, so in this case, goose. And then it's getting our data set dictionary, which we can look at in a second, but that's really just, or this is making a variable data set dictionary from our data set train. You'll see what this looks like. This is just all those data annotations like we saw before in the Cocoa format, but now it's in another JSON type format in a Python dictionary. And then here, we're really just getting 3 random images and making sure we're using the visualizer functions. We're making sure that they're imported and drawn correctly. So we imported this in. This looks correct to me. We even got a cute images of baby geese here, which hopefully, I think they're going to have babies again soon. I think it's almost a year exactly of when I took this image last year. So you can see that these images look like they're labeled correctly. It's really important to do this, especially if you're building your own data reader. Like if you're not using a pre-built thing like Cocoa, it's really important to make sure that you're reading in the data correctly, because I've done this before where I was like, sure, I read my data correctly, and I was wondering why my model wasn't training, and I made the mistake of not looking at it when I imported it in. And sure enough, when I did go look at it to troubleshoot it, it was like somehow I read in my rectangles inversed or something, and they weren't over the objects I was actually trying to train on. So the model just didn't understand what to do and never worked. And then I fixed it, and then it worked fine. So if we look at our dataset dictionary, you can actually see this is what it looks like now. So we have our annotations of those bounding boxes, just the rectangle coordinates, as well as like where it ties to. So like back to this specific image, and then we can do things like draw, or when it comes to our deep learning model, train just on this specific area. So now we'll run this. So I have a link. I won't share the link in the chat because most of you should probably be in the notebook or at least have a copy of this now set up, and you can go click on these later. One thing I don't like about Detectron 2 is it doesn't have a built-in way of easily running data validation. And I'll talk about that in a second as we get to the training. But this is what this is doing, is really setting up a specific class that we can do data validation. Essentially, we're going to evaluate how our model is performing as it's training. So I'll talk about that as we train our model. So just run that code cell and then go ahead. Let's run this one. It might take a while. So I'm just going to make sure it's running, and then I'll go through what's happening as it's running. So this is actually doing the training. So this is where the machine learning part comes in. We'll see some output. This is actually a structure of a convolutional neural network. And I could talk more about this in a bit, but I'm going to scroll up and talk about what the code's doing, and then we'll look at the output. So here I have some other links to like the official Detectron 2 documentation, as well as a thing called Model Zoo. So the Model Zoo is a place where you can go look at all the pre-built models that are in Detectron 2, and which one do you want to use for object detection or instance segmentation or feature points, et cetera. You can go choose some different types from there. And then this is how we set up our Detectron 2 configuration. So we import something called default trainer. And then this is kind of just the way you do this here. So we have a config variable called CFG. We say get config from Detectron 2. And then we're saying merge file from model zoo, get config file. This is where we select our architecture. So we're saying in this case, we're going to do COCO detection. So we're going to do rectangles, not instance segmentation. And we're going to use a faster mask RCNN with a, I think this is a 101 ResNet, but there's a couple of different options like a 50, so smaller classification architecture. So your model might be able to run faster on more limited hardware. And then down here, this other version, you want this URL to be exactly the same as this, otherwise it won't work. But this is where the transfer learning comes in. When I was saying most architectures have pre-trained models and pre-trained weights, we're essentially setting our checkpoint to this. So this is our starting point, and then we're going to pass our new data into it, and it's going to adjust the weights in the neural network. And you'll see it actually won't take that long, and we'll get a really accurate model because we're doing transfer learning. Otherwise, it would probably take way longer. So just remember, if you change this out, so I actually have some common ones up here. So if you wanted to do instance segmentation, you could actually just copy this URL into this part, this little string here, but you want to do it for this one as well if you're doing polygon labeling and instance segmentation. And then here, this is a very important variable for you to remember. So if you're training your own model after this, this is how many different objects you labeled in your training data set. So in this case, we're only looking for geese, so it's 1. But if we're doing geese and ducks, that would be 2. If we were doing geese, ducks, and boats, that would be 3. So it's important for you to change this as well. And then this points to our training data set. You can actually add multiple training data sets in here if you had them separated for some reason, like different people labeled in different projects. You could pull them in here as long as they were imported in from where we did that COCO, when we read in the COCO data set. And it's also very important to have this comma here. If you do some editing and you change this string out and you delete this comma, it'll throw an error and it's not immediately obvious why, but it's expecting this comma because it makes it a tuple versus just a string being read in. And so if you are missing that and you get an error, just add it back. And then we have our max iterator. So this is how many cycles we're going to look at our data set. So in this case, we're going to read in our data set 300 times. Learn from it each time. We're going to make predictions and then see how well our model did, or this is what the model's doing. We're not doing it manually. We're seeing how the model's going to see how well it did, make some adjustments, and then hopefully learn from the data and get better over time. We have something called a base learning rate. You can read more about learning rates later. This will probably be good for a lot of different data sets, but it's something to look at that you can adjust. And it's just kind of how your neural network learns, how big of steps it takes in different directions. You can read more about that at a different time. And then we have some other advanced options you don't really need to worry about right now. But if you want to do anything like distributed computing across multiple GPUs and stuff, you can do all those things in here. But most likely you could just leave these as default for now, unless you really know what you're doing and you want to mess with these hyperparameters, you can. And then we're making a new output folder called output. We'll see that in a second. That's where our model is going to be saved to. And then we are reading our dataset validation. And then every 50 cycles of going through our dataset, we're going to read in our validation dataset and run predictions against it. So the way that the train, test, and validation works is that we're reading our training data, and that's how the neural network is learning about what to make predictions on. But pretty much all the time, like as long as you're reading the data correctly and your neural network is like created correctly, it's almost always going to get better at predicting the data that it's looking at, right? Because it's learning from this data set, and it's going to get really good at detecting geese in those specific images. But what you want to do most of the time is make sure that your model is going to generalize well on images it's never seen before. So the validation data set, it's not actually learning anything from it. It's just making predictions. And then you as a human can see how well your model is doing as it's training. And then maybe you want to stop the model, tweak some of these hyperparameters, add more data, different things like that. Maybe you need more epochs or iterations through your data. So the validation data set is almost really a training data set for you as the human in the loop to make sure that your model is working correctly as it's training, and then you can adjust things. Once you feel like your model's in a great point and working good on the validation data set, then you can test it on the test data set later after you've already made your adjustments. So I'll show you what that looks like in this output here. We have a whole bunch of stuff. Again, this is kind of the architecture of I think this is a ResNet convolutional neural network. And then you can see it read in our Goose data set, and there's 260 instances. So there's 110 images. Most of those images have way more than one goose in there. And then we read them in at the COCO format. And then you can see, don't worry about these. It read in our validation data set. And then it's going to start learning. And where is in the output? So here you can see that it has all these metrics. Typically, a lot of times you want loss to go down in deep learning and things like accuracy to go up, or other different measurements of accuracy kind of to go up, and loss, which is it's a loss function of how your neural network is learning. You always want that to go down. So as you look at this total loss, it should always be going down. But this is on the training data set. And what's really important is to make sure that this number, this is on that separate validation data set. We want this number to go up. So this is AP, which stands for average precision. And there's kind of different various ways of doing it. So you can see like some different metrics here. And I actually have a link later that goes much further into all these different metrics for things like object detection. But you can see it's 25 here, which isn't great. You know, like I think an average precision of like 50, well, it's a little different for average precision versus like accuracy. But if you had an accuracy of 50%, that's essentially random, right? Average precision is actually about where those bounding boxes are drawn. So if they overlapped, you know, a lot and were basically intertwined, that would be a high average precision. But if it's doing a bounding box over here and the real bounding box is over here, that's going to be a very low average precision. So you can see it's very low right now. And then after 100 epochs is 37. And then it jumps up really high to 66 and then keeps going up. And then by the end, we're at 83, which is pretty good, especially for just how quick we train this. And then we can run this next cell TensorBoard. Occasionally people do tell me this doesn't work on their Colab notebook, and I have no idea why, but if it doesn't work, don't worry, it doesn't affect any other part of the workshop. So first of all, let me know, did your model train? Or is it still training? Sometimes you get not as good of a GPU when you come onto Google Colab, and it can take longer. So occasionally people will still be training, but also let me know if you finished training a model. Someone said how TensorBoard can integrate with current training. So if you're running this on your actual computer, I don't know how to do this in Google Colab. I don't know if you can. Most of the time you can run TensorBoard as like another process from your terminal or something like that. And you can actually see this live as it's going, which is really cool. So instead of looking at this text output, you'll actually you can look at this graph and see it's still going up, or, you know, the loss is going down or whatever. I don't know if you can do it in Colab simultaneously. I haven't figured out how to do it. So someone said they finished training, average precision 82. Awesome, very cool. And I'll have a link more about average precision in a second. But so you can see we open up our tensor board and we can see our average precision going up over time. And it looks like at the end, it's still jumping up and it's still going up. So if we trained our model for more, it actually might be more accurate. So it's great to look at this chart to kind of see where you're leveling off. Like if this went up and then just became a straight line after a while, we could say, oh, well, we could have stopped training a while ago because it looks like it really just kind of plateaus in how good it gets. But if it's still going up, you might want to train longer. And there's a whole bunch of other stuff you could look in here. So if you want to look at like loss and all of this other metrics that you could look for, you can see it in the tensor board. All right, so let's go ahead and use our trained model. If we look in our output folder, we can see that now there's a model final.pth, which is a PyTorch extension for a saved model. Let's go ahead and run the cell. This is essentially we're setting up our model again, but we're not training this time. We're just saying, hey, we're creating we're reading in a model, and it's this type of architecture. So this needs to be the same architecture as what you trained on. If it's different and you try to read in the model, it just won't work because this needs to know, hey, this is the architecture that we want to run our model on. And then instead of loading in the pre-trained weights from Detectron2, we're now going to load in the weights that we trained. So we can actually just always set up new models, bringing in our weights here, our trained weights. And then we're going to bring in my test data set here. We'll use this in a second for some metrics. Again, this is important. If you trained with more than one class, you'd want to adjust this number here. So again, if it was goose and ducks, that would be 2. If it was goose, ducks, and boats, that would be 3. A lot of times you'll have more than one class. It won't just be one. So you want to adjust this number as well so it knows how to read in your weights and make correct predictions. And then this is important too. So this is the threshold at which it will make a prediction. So currently with this 0.9, it's going to say, hey, you have to be 90% confident that it's a goose in this case, or whatever you were trained on, to return a prediction. So if you are training on a much more complex data set, your model might not be at that 90% confidence level. So you could lower it down. If you do this and you run it on a test image and it's not working correctly, you could just go and lower this to 70% or something until you see some model, see some predictions drawn. So we'll leave this at 90 for now, but it can be important to know how to lower that. Then we have our predictor, a variable that we're making, so we can feed in an image and then get predictions back. And we'll see that right here below. So we're going to read in a test image. And this is actually from the test data set. So it's never seen this image before. And it wasn't in our validation data set. So we have no idea if it's going to work well or not. And then we're reading in with CV2, which again is OpenCV. And then we're passing in the image to our predictor. And then we're writing out our visualization. And this is actually just flipping the color around from red, green, blue to green, blue, red, or vice versa, because OpenCV actually reads images in red, green, blue versus RGB like most other libraries. So you have to reverse those coordinates. And then we're getting metadata. So this is really just saying like, what classes are in our data set. And then we're writing out a scale of half the scale. So instead of this image being really big, it's half the size. Then we're drawing our output with this draw instance prediction. And I'll show you what's actually happening here in a second. So you can see if this worked, congratulations, especially if you've never done anything with computer vision before, because it's your first computer vision model, if that's the case. And it's an awesome one. Like it's really accurate on detecting geese in a park background, at least. I can talk about that later as well. But you can see it's working well. Hopefully you got this far. Let me know in the chat. Were you able to train this model? And is it working on this picture? Adam said yes, super exciting. Sorry, so we printed the image that we read in. You can actually see it's just a multiple dimensional array. And these are the red, green, blue colors for each pixel essentially. Oh, and so someone had a great question. Sorry, I did not mention that. So currently it says tensor 0. I believe that's because the class is 0. And for whatever reason, the draw prediction here just isn't set up to grab the class from the metadata. So like a 0 would be goose in this case. If we had a goose and duck one, it might be 0 is goose and 1 is equal to duck. But actually, we'll get to a point where we'll draw them out with the goose label on them in a video, and it works great. But really, the most important thing is let's look at these predictions. So we passed the image into our predictor, made a variable called outputs, and then we'll look at the outputs. And you'll see this is a common thing in PyTorch where it says like 2 device, like 2 CPU or 2 GPU. That's because we made the prediction on a GPU because it usually runs faster than a CPU. But then when we're doing stuff like drawing it out or doing something with that information, we usually want to move it back to the CPU to do things on that. So if you ever see something like 2 whatever or 2 device in PyTorch or Detectron 2, that's what's happening is you're just moving data from the GPU memory to the kind of CPU area. So if we print this out, this is actually the really important stuff. We see that there's, it detected 2 instances, which is already important. If all you're trying to do is measure how many animals are in a frame of your video, this could already do pretty much everything you want. Like, hey, there's 2 geese here, like send me a text or whatever, whatever you're looking for, cats or whatever your use case is. We have some other metadata about the images. And then here we have some fields. We have our predicted boxes. And these are the bounding box coordinates. So this is how, where to draw here. And I think this one is the second one, where to draw here. And then it says scores, which is 99 and then 98. And then we have predicted classes, which is our tensor 0. Again, everything is zeros in this case, but it could be 0s and 1s and 2s and 3s, and however many classes you have. And Python, like most programming languages, start at the index at 0. So 0 is the first item, which is pretty common. I think a few languages don't do that, but Python does. So 0 is just like, this isn't the first class that I'm making predictions. But this is actually the really powerful stuff here because, yeah, like as humans, we love to visually see these things drawn out, right? But if you're doing like an algorithm or something after you're doing a prediction, chances are you're going to use this data, right? Like you could see, hey, do these bounding boxes cross over each other? How close are they to each other? What's the accuracy? How many are there in a frame? So like here, we're just going to get the object count real quick. Detected 2 geese. And this will dynamically change depending on how many detections there are. So this is where you can actually make a lot of those decisions. Or like if you do a prediction from one frame to the other, you could see like, how much did the bounding boxes change, use that information to do some sort of object tracking. A lot of cool stuff in there, not just writing out visualizations. But let's do it again on one more other image. You can see detecting geese, again, pretty high confidence. And there is a story behind this data set and why there's geese photoshopped in my living room. And I can talk more about that later, but it's kind of like creating, actually, let me just bring it up real quick right now. So if you're creating a data set and in this case, all these pictures of geese were taken in similar backgrounds, like with green grass and stuff like that. And it did a really good job at detecting geese in this same setting. But if I was running a model in my living room, it might detect this chair as a goose and stuff because it's like, hey, there's a something in the foreground or there's a background. And so I want to essentially you want to make your data sets pretty diverse, where it's going to have every variation of backgrounds and different objects inside the training data set versus just all in one setting. So if, for example, this goes back to actually, like I talked about the Amazon Go example, where it's like training to detect people in the winter versus the summer, the data varies. So the same thing can happen with backgrounds. So if this is all green right now, but then we're detecting geese in the snow, our model might not be good at that if it didn't have that different background variation. So it's important to collect kind of all the different variations of data. And I can talk more about that later, but let's continue on. We're almost done with the coding section, and I will be hanging out and answering any questions afterwards. So let's just get through this, and then we could go follow up on anything you want. So here, we're going to run some metrics on our separate test data set that we did not look at yet. We're going to get that average precision again, but on a completely different data set. So if we did a lot of tweaking while looking at our validation metrics, we would want to make sure, hey, this is still going to work on data it's never seen. and data that I didn't look at to make any decisions based on my model. So you can see average precision is almost 82 again. It's 81, pretty great. Now let's run it on a video. So it's way more fun having these drawn out on like a whole video that you can share. It's really cool. So here I'm going to import YouTube video, and it's just displaying. I just have a short little goose video here that I took. And then we'll pip install YouTube download. It allows us to download a video from YouTube, which is going to be that goose one. And then we'll run this. This is going to download my video. Now you don't have to run this code cell for this workshop, but I left this in because what this does is it creates a clip from that video. And this is nice if you're going to run a model on a video that's like several minutes long. It can take a while to write out each frame with predictions. So sometimes if I'm doing visualization on a much longer video, I'll actually clip it to like 6 to 4 seconds to make sure that it's working how I think it should work, instead of waiting like 20 minutes or something for it to write out a video on a long, write out the prediction video on a longer video. So I left this in here, and this is just creating a video clip from the video.mp4, which is what we downloaded here. And then if I wanted to run the next cell on this clip, I would just change this path out to that video clip.mp4 right there. But I won't do that here. I'm just going to go ahead and run this, and then I'll talk about what's going on. It will take a minute to run. You can see it's giving a little count at what percentage it's at. Essentially what this is doing is it's just reading information in from the video. So we have this video.mp4, we get the width, the height, the frame per second, the number of frames, and then we're creating a variable called video writer, which uses the video writer function of OpenCV. We're going to write it out to out.mp4, and we're going to, you can define things like frame rates and everything here. We're essentially just keeping it the same size as the original video. We're creating something called video visualizer. And we're getting the metadata from the data set. This is where it's going to get the names of like goose and stuff. So it's actually going to write out with goose, not just tensor 0. And then here's a function we have. Essentially, it's just saying while there's still frames left in this video, go to the next frame, like read in a frame, take that frame, draw out those predictions, just like we did with the image before. Except for we're going to yield that frame out of this loop and then use the video writer function to kind of string all these frames together. So essentially what this is doing is just saying, hey, well, there's frames left in this video that we didn't read yet, read it in, make a prediction on it, draw out those visualizations, and then yield that visualization out that we can stitch it together and create a video. And then we have this library called TQDM. If you've never used it before in Python, it's really cool. It actually allows us to create this neat little visualization here. So if you're doing something like cycles, like I've done this, if you're creating a custom training function in PyTorch or something, and you want to see the percentages done, you can use TQDM for it, which is a nice little thing because they don't do that by default in PyTorch. We're almost done here. And then this is just downloading the file. Occasionally you might get a pop-up that says like, hey, do you want to allow Google Colab to download a file? And you can just say yes. And it's downloading our out.mp4, which was the setting we have here, right? We're saving it as out.mp4. And then hopefully this works for everyone. How's it going for everyone so far? The chat's been kind of quiet. So hopefully everything's going perfect. Usually it's a good sign because there's no errors, but I just want to check because it's a little more quiet than normal. Someone said they're still stuck at training. Oh, crazy. That's a long time. All right, so I got my output and I'm going to open this up. And ta-da! We have our object detector running on this video, or it ran on this video, and we drew the outputs out. And you can see it's doing a really good job. So congratulations again, especially if this is your first time doing computer vision, because we actually went through from, how to build a data set and doing all the labeling to actually training a model on that data set, which is a lot. So I know it was a lot to take into, depending if you've ever done anything like this before. So if anything was confusing, just keep at it. And I'm going to stop the recording, but I will be sticking around and answering questions and hanging out. So if you have any questions or you want me to go over anything again, I will do that here.